Today we have José Miguel Urbano from the old and beautiful University of the old and beautiful city of Coimbra, who, by the way, is a frequent visitor of Brazil and has a lot of connections here, so we hope it will keep and even develop even more. So don't hesitate talking to him. And so without more introduction, thank you, and please.
Okay, thank you for the introduction, and thank you to the organizers for the invitation, of course, but especially for such a wonderful organization of this conference. So I'm going to speak about a few problems I've been studying in the last couple of years, some of them with people from Brazil. And so they concern regularity for singular and degenerate PDEs. And the focus is not so much in qualitative aspects of the theory, but more on quantitative types of results. So we are not concerned with saying that, for example, a solution of a certain PDE or of a certain free boundary problem is, say, Holder continuous or continuous, but in determining exactly what is the Holder exponent or what is the models of continuity for this solution. So I'm going to talk about three problems. The first two I'll only mention briefly. So this is only a bit of advertising of what we've been doing. They are already published, the results. And I will concentrate more on the third problem, which was solved only recently here in Brazil, by the way. So the first problem was solved with Eduardo Teixeira from Fortaleza and concerns the precise Holder exponent for the solutions of the p-parabolic equation in the inhomogeneous case. And the second one is a derivation of a sharp modulus of continuity for the solutions of the two-phase Stefan problem. And this is joint work with Paolo Baroni, a young Italian mathematician from Scuola Normale in Pisa, who is now in Uppsala in Sweden, and Tuomo Cusi from Aalto University in Helsinki. So the first problem is this. So we know since the 1980s that solutions of this p-parabolic equation with f satisfying some sort of integrability condition are of class C0 alpha. They are Holder continuous. The problem with this PDE is that it is degenerate. I'll only talk about the case p greater than 2. And so this means that the modulus of ellipticity of the equation vanishes when the gradient is 0, right? When you try to adapt the theory of the Giorgi for this PDE, the problem is not so much that we have here a nonlinear principal part, right? The method of the Giorgi is a nonlinear method. The problem is that this term grows nonlinearly with respect to the gradient. So the Russians, Ladizhenskaya, Uraltsev, and Solonikov, they knew how to do this, how to prove the Holder continuity for a nonlinear principal part that would grow linearly with the gradients. But when you have a nonlinear growth, this could not be done, and the reason is very simple. When you write the Katsopoli estimates for this problem in this setting, these estimates are not homogeneous. So you get two different powers, power 2 and power p. And this is what precludes us from using the method. So the idea of Di Benedetto in the early 1980s was to write this iteration. So basically what you have to do to prove Holder continuity is to estimate the reduction of the oscillation in a sequence of nested cylinders, say. And people were trying to do this in what seemed to be the natural cylinders. So this is space and this is time. And if you have here r, the scaling of the equation tells you to use r to the p here. Now, if you write the Katsopoli estimates in a box like this, as I said, they are not homogeneous. So the idea of Di Benedetto was to do them in a box, in a cylinder, that has to be stretched according to the solution itself, right? So basically what you have to do is to multiply here in the time direction by a factor. So, and rewrite the estimates in these stretched cylinders. Right, the scaling factor is basically, it's essentially omega to the 2 minus p. So a very large number when omega is small. And when you do this, when you rewrite the Katsopoli estimates in these stretched boxes, what happens is that the estimates become homogeneous. So you only have power p, right? So the problem somehow becomes elliptic, right? And then you can use your favorite embedding theorem and carry on with the proof, right? So this was the idea. Now, the technique is very beautiful, but there is no hope whatsoever of keeping track of all the constants that appear along the proof. And so there's no hope of determining the alpha there, right? So all you know is that there is some alpha, very small alpha, such that solutions are C0 alpha. So we used a completely different approach to this problem. Before we proceed, let me mention this notation. So Q here is the integrability in space of the source of the right-hand side, and R is the integrability in time. So we need to make some assumptions on these two numbers. So first of all, they have to be sufficiently large. Otherwise, you cannot write the Katsopoli estimates, and you don't have Holder continuity. So the first assumption you have to do is this one, right? But you don't want them to be very large because, if this is violated here, then you enter a different regime and solutions are in fact C1 alpha, right? And if they are C1 alpha, it doesn't make any sense to try to determine the optimal Holder exponent, right? Because solutions will be Lipschitz. So you want to keep R and Q in this range, right? For example, if Q and R are equal, this just means that Q has to be less than the parabolic dimension n plus 2, right? And for those of you more familiar with the elliptic case, this is the restriction on the integrability of the right-hand side. So it has to be larger than n divided by p and smaller than n. So what we proved was this, that for the non-homogeneous problem with these assumptions on the integrability of the right-hand side, the alpha is precisely this number here. So you determine exactly the alpha only in terms of p, the space dimension n, and the integrability of the right-hand side, so the q and the r, right? Well, this looks a little bit miraculous how this comes up, but if we look at it in this way, so we can write this number in this form. And if you write it in this form, it's a little bit more acceptable because you see, exactly the two restrictions that we did on the exponents. So you see all these factors here are positive, right? Because this here is less than 1, and this here is larger than 1. And so this is, of course, positive. And obviously, since this and this are the same, and this is positive, this is also less than 1. Okay? Moreover, if we project this into the linear setting, we obtain exactly the alpha that is known to be the optimal Holder exponent for the non-homogeneous heat equation, which is exactly this number, right? This was obtained before by other methods. And also, if f does not depend on time, so in the elliptic case, the alpha becomes this number, and this is also the optimal for the elliptic case, and this was obtained by Eduardo previously. Okay. Finally, let me mention that we can look at the behavior of the exponent as p increases, and it is, in fact, alpha is an increasing function of p. So as p becomes larger, alpha becomes larger, and as you would expect, when p goes to infinity, the alpha goes to 1, right? Some indication that, of course, for infinity harmonic functions, you get Lipschitz regularity, right? Okay, so the method is based on this idea of geometric tangential analysis. So basically what we look at the homogeneous problem as being tangential to the non-homogeneous problem, and we somehow import the regularity of the solution of the homogeneous problem to get the regularity of the solution of the non-homogeneous problem, then we have to correct according to the scaling. And that's where the alpha, it's how we derive the alpha exactly. So, in the third problem that I'll mention in detail with proofs and so on, we use the same technique. So let me stop here with respect to this. So the paper is published in Analysis and PDEs. So the second result I want to mention, joint work with Baroni and Cusi, has to do with the Stefan problem. So for the younger people, let me just briefly recall what happens here. Suppose you have a unit mass of ice, and you heat it, and you look at what happens to the temperature. So if this is, say, energy, and this is temperature, when you hit the system, the temperature goes up until it reaches 0. Then you continue to heat, and the temperature remains constant for a while. And then when this amount of energy has been absorbed by the system, then the temperature goes up again. Right? And this is what's called the latent heat of the phase transition. Right? Let's call it alpha, lambda, sorry. Now, so basically when you want to solve the problem, so you have a domain here. You have, say, the liquid phase and the solid phase. This is the free boundary, so it's a priori unknown. And you want to solve the heat equation on each phase. And then you have conditions on the free boundary, namely that temperature is 0. And then you have a balance of heat flux is saying that the jump of the gradient of the temperature is proportional to the velocity of the free boundary. Right? The way you formulate this problem in a weak sense is this. So this is the way you formulate the problem. This is the Heaviside graph. So if you invert this thing, right, and you write, so here, energy or enthalpy with a function of the temperature, you get something like this, right? And so the time derivative is not the time derivative of the temperature, but the time derivative of the energy or the enthalpy. And so this is a choice in this maximal monotone graph. Right? That's why I have here this inclusion. And this is formulated weakly in this way. So again, the problem is singular because, roughly speaking, this guy, the derivative of this guy, is infinity at 0. Right? So that's why the problem is singular. And so this was studied in the early 80s again. Also for more general structures, so you can have a principal part. Again, here you must have a linear growth with respect to the gradient, and you can also replace here u by some beta of u. So this doesn't have to be the identity here. You can have some function. So for the one-phase problem, so when u is constant on one side and positive, the modulus of continuity was obtained by Caffarelli and Friedman, and it looks like this for n greater or equal than 3, and it looks like this for n equals 2. And for the two-phase problem, again in this general setting with the principal part that grows linearly with the gradient, this is the modulus of continuity. And this was obtained independently by Di Benedetto for these general structures and by Caffarelli and Evans for the case of the Laplacian. Now, this modulus is not written explicitly in any of these two papers, right? But, you can, looking carefully at the analysis, you can really see that that's the modulus that is shown to hold in these two papers. So what we did was to improve this in 3 ways. So the result is this. So we consider, again, a principal part that grows non-linearly with the gradient, right? So we combine a singularity in the time derivative with a degeneracy in the principal part. And so we obtain this modulus that we're not sure it's optimal, but we conjecture it's optimal. We're still trying to find a counterexample to show that you cannot improve this. So, I mean, it holds for any p, not only for p equals 2. That's one improvement. The second one is that we determine exactly this exponent here. It's p divided by n plus p. And probably the most important improvement is that we got rid of one log here, right? So it's just one iteration of the log. So let me now, for the rest of the talk, main part of the talk, now with proofs and with every detail, speak about the CP prime regularity conjecture. So now we are in the elliptic setting, and so we have this degenerate equation minus P Laplacian of u equals f bounded. So this is a joint work with, again, with Eduardo and with Damião Araújo from Florida. And so the conjecture says that solutions of this equation are C1 alpha with alpha equals 1 over p minus 1. So that's why it's called CP prime, because 1 plus 1 over p minus 1 is p prime, right? Now, this is clearly the best you can hope for, because we have this explicit example, this explicit solution, right? And this is CP prime and not better than that, right? So this sets the limits to what you can obtain. And the conjecture is that this is, in fact, the optimal regularity. Now, to see that this is a delicate issue, let's see what happens in the linear case, right? So we know that solutions are C1 alpha for every alpha, but they are not C11, right? So the conjecture does not hold if p equals 2. If p equals 2, it's not true that solutions are in C11. So the best you can get is C1 log Lipschitz, right? Log Lipschitz is this. So the models of continuity is sigma log of 1 over sigma, right? So, I mean, if a function is log Lipschitz, then it's C alpha for every alpha, but of course it's not Lipschitz, right? So the reason being that, I mean, if we have this, right? So right? Is this right or the other way around? No, this is correct, right? No, it's the other way around. Sorry. We are close to 0, right? Okay. Now, I mean, we could only do it in 2D. And in 2D, there's already this result very recent result by Lindgren and Lindqvist. And they have an asymptotic version of this. So they show that solutions are in CP prime minus epsilon for every epsilon, right? But I mean, going from this asymptotic estimate to the sharp result, I mean, it's far from trivial, as we've seen in the linear case, right? And what we need really is a very sharp control of the oscillation of a solution in terms of the size of the gradient. So you see, this is the main tool in the proof. Now, why is 2D special? Now, our proof is not a 2D proof in the sense, for example, of Savin's proof of the C1 regularity for infinity Laplace, for infinity harmonic functions. We could only do it in 2D for this reason. We need some room with respect to the regularity of p harmonic functions. So this means that in general, we only know that solutions of the P Laplace equation are in C1 alpha. This alpha depends on dimension and the P. But we don't have information about this alpha, about what is this alpha exactly. And we need this alpha for the proof to work, to be larger than 1 over p minus 1. Right? So in fact, what we prove is this. If p harmonic functions are in C1 alpha with alpha larger than 1 over p minus 1, then solutions of the non-homogeneous problem are in Cp prime. Now, in the plane, we know more, because we know exactly what is this number. This is a result by Ivanic and Manfredi, and they show that in 2 dimensions, the alpha of the C1 alpha regularity for p harmonic functions is this number exactly, right? And again, this is a typical 2D proof, right? They use the autograph transformation and so on, right? So what this means is that we have room, is that p harmonic functions in the plane are C1 1 over p minus 1 plus a positive number, tau 0, right? I plotted here the alpha to p in terms of the p and the 1 over p minus 1. So for p greater than 2, there's always room here, right? Of course, this guy goes to 0 as p goes to infinity, and guess what's the limit of this when p goes to infinity? It's 1/3, which is exactly the regularity that we expect for infinity harmonic functions, right? But of course, this is not a proof because the estimates blow up when p goes to infinity, right? But this, of course, when p goes to infinity, this goes to 0, this goes to 1, so this is 1 plus 1, 2. So this is 2 over 6, which is 1 over 3. Okay. So what we prove is this. Again, if this number, which is the Holder exponent for the C1 alpha regularity for p harmonic functions, is larger than 1 over p minus 1, then solutions of this equation are in C1 1 over p prime, p minus 1, right? So Cp prime. The conjecture is true. So, and as I said, the proof is dimension free, right? So the fact that we can only do it in 2D is because only in 2D we know that this is true. In higher dimensions we don't know because we don't know the value of this number. Okay? So now the proof. The first thing we need, the first ingredient of the proof, we need a way to connect the regularity of solutions of the non-homogeneous equation with solutions of the homogeneous equation. Right? And this is what we called existence of C1 small correctors. So what is a corrector? Suppose we have a weak solution of the equation with the L infinity norm less or equal than 1. We show that for every epsilon there is a delta, depending only on epsilon and the data, such that if f in L infinity is less or equal than delta, then we can find a function, a C1 function, which is small in the C1 norm. This psi and the gradient of psi are less or equal than epsilon, such that u plus the corrector is p harmonic. Of course, in a ball with half the radius. So this is how we link the theory for the homogeneous and the non-homogeneous equations. Now, this proof is standard, it's by contradiction. I mean, you suppose this is not true, and then you build a sequence. You have a compactness, pass to the limit, get a contradiction. So I'm just going to jump this. Now, a note about this, say, smallness regime that is mentioned here. So if we have a solution of this, then you can build a new function v, which is obviously normalized. You build it in this way, so this theta is this number. And this v solves this equation, right? And this, of course, the right-hand side is less or equal than delta 0 as you want. So the smallness regime is not restrictive in a way. So you get the results for v, and then from that you get the results for u. So as I said, what we need to do is to control the oscillation in terms of the size of the gradient. And the first lemma we're going to prove is this. So we show that there exists a number, lambda 0. This number is universal. It only depends on the data. It does not depend on the solution. And delta 0, so this is very important, that these two numbers only depend on the data, such that if the right-hand side is less or equal than this delta 0 and use a solution, always with this condition on the L infinity norm, then the distance of u in the L infinity norm to this first order approximation is controlled by lambda 0 to the p prime. So the proof is relatively simple. So you take epsilon to be fixed later. But this epsilon, I mean, it's a number that does not depend on the solution. So it's a universal constant. You'll see later. I just don't write it immediately because it could come out nowhere. And then with this epsilon, you apply the previous lemma to find the delta 0, right? If epsilon only depends on the data, delta 0 only depends on the data, right? Because the delta only depends on epsilon, p, and the dimension. And, sorry. So apply the lemma under the smallness assumption on f and obtain a corrector, psi, right? So as this function u plus psi is p harmonic, by Iwaniec-Manfredi, it is Cp prime plus tau, 0, for a positive tau 0. And now in this ball, which is contained in the ball of radius 1/2, the ball of radius lambda 0, which is smaller than 1/2, we estimate this difference, right? So what we do is just we add and subtract the linear approximation for xi, and these three guys are controlled by epsilon because this is a small corrector. And here, you just use the fact that u plus xi is in Cp prime plus tau 0, right? To bound this difference in this way. And now you make the choices. So first, we choose lambda 0 small enough such that this holds, such that the first term here is less than 1/2 lambda 0 to the p prime. You see, this is possible only because we have room, only because we have here this tau 0, right? So since this power is larger than that one, we can always do this choice, and this only depends on the data, right? And then once you have the lambda 0, you write the epsilon like this. So if you put these two things together, you get 1/2 of lambda 0 to the p prime plus 3, 1/6 lambda 0 to the p prime, so you get exactly 1/2 plus 1/2, you get this, okay? And the choices are completely independent, so the epsilon is fixed, so the delta 0 also does not depend on the solution. So everything is okay. So this is the first lemma. Now, what we want to do is to iterate this, right? But, so you see, it's not in this case, when we're doing Holder estimates, you can immediately start iterating. But now you don't have u minus u of 0, you have u minus some affine function. It's not clear if this affine function satisfies a PDE of the same type, so you cannot iterate. But it's a trivial corollary of the result that you can write this, right? It follows from here immediately, right? That the sup of u minus u0 is less or equal than lambda 0 to the p prime plus the modulus of the gradient of u at 0 times lambda 0, right? And this is what we're going to use to start the iteration. So now the main theorem, which is this. So under the same assumptions as before, there is a constant, depending only on p, such that this holds for every r small enough, say. Okay? So we estimate the oscillation of the function in terms of the size of the gradient in this way. Let's see how the proof works. So we have these universal estimates, the universal constants. They are already determined, the lambda 0 and the delta 0. And the lemma holds for u. So now we define this new function v in this way. So v is this function, so a constant here, u lambda 0x minus u0. And we see that the L infinity norm of v is less or equal than 1. This is just a consequence of the lemma, right? Because that's exactly what the lemma is saying, the lemma that holds for u. Moreover, v of 0 is 0. The gradient is this, right? Of course, this is a constant. This comes out, the lambda 0. And v solves this equation. So minus p Laplacian of v, I mean, this comes out as lambda to the p, and this comes out with power p minus 1, right? So then you estimate in this way. You get rid of this guy. This becomes larger. And then p prime multiplied by p minus 1 is p. So this here is 1, right? And the f is less or equal than delta 0. So v is now in the conditions of the lemma. And we can apply the lemma to v because of this, right? So you apply the lemma to v, and we get this, right? No, the corollary, this corollary. Applied to v, we get exactly this. And now we rewrite this in terms of u, right? So we replace here v by its value, right? V of 0 is 0. So this is v here, right? And this is the gradient of v at 0, which is this number, right? And then, yeah, and then we multiply, right? We multiply by this. This cancels out this guy here. And we get, so lambda 0 to the p prime times this, plus lambda 0 squared times the modulus of the gradient of u, which is what's written in here, okay? So this is the first step of the iteration, okay? And then we do it again, right? So you define this sequence. So you call ak the soup of u minus u at 0 over these balls of radius lambda 0 to the k. bk is ak divided by this number. And so we get this recurrence relation here. So ak plus 1 is less or equal than lambda 0 to the p prime ak plus the gradient of u at 0, lambda 0 to the k plus 1, right? And now we estimate. So bk plus 1 is by definition this guy, right? You replace here, you estimate using this. So lambda 0 to the p prime ak, so this is exactly what's in there. And then you see that this divided by this is just bk, right? You get ak lambda 0 to the k times p prime, which is bk, plus the gradient lambda 0. I mean, this is just nothing, okay? And now, yeah, and now, this is more elaborate, this part. So now you take any r, small enough, right? And you choose a k such that r is between lambda 0 to the k plus 1 and lambda 0 to the k, right? And this is what you want to estimate, right? So here, from here to here, you use this fact. So this is smaller, so this is larger when you put here a smaller number, right? And this is exactly, so the soup in this of u minus u at 0, it's ak divided by lambda 0 k to the p prime. This is bk divided by lambda 0 to the p prime, okay? And then you use this, this estimate k times, right? You use this k times and you get b0 plus the gradient of u at 0, and then you get this sum, right? And then what you tend to do when you get an expression like this is to estimate this by the sum of the series, right? But the series is divergent, so you cannot do it. But okay, so you know how to sum this. It's exactly this number, so it's the first term. So it's the ratio to the number of terms minus 1, the ratio minus 1. Okay? So this is exactly this sum, right? You don't estimate. You just write it here. And so you estimate afterwards. So this is what we have, and now we're going to estimate here, the right-hand side. A0 is less than 2, right? Because it's u of x minus u of 0. U L infinity norm of u is less than 1, so it's just 1 plus 1 is 2. This guy is here, and here you get rid of this minus 1. Okay, this disappears. And you have here a number. Right? That's what I did here, right? I just got rid of this minus 1. And everything else is there. So this divided by this multiplied by this guy, okay? And now you see that this here is a constant that only depends on lambda 0 and p prime, so only depends on the data, right? This is 2, so you get this constant times 1, right? This is just the largest of 2 and this guy, okay? 1. You get here the gradient of u as 0, and then here you use the other inequality here, right? So now you use the fact that r is less or equal than lambda 0 to the k. So here when you have lambda 0 to the k, you replace it by r, and you get something larger, right? And this 1 over 1 minus p is just minus p prime minus 1, right? So minus p prime minus 1 is 1 minus p prime. It's exactly 1 over 1 minus p, okay? So passing the r to the p prime to the right-hand side, we get exactly the estimate that we wanted, okay? So now, finally, so this is the main ingredient to do the proof. What we want to show to get the C1 1 over p minus 1, the Cp prime conjecture, we want to show this, right? That for every r, the sup in the ball of radius r of u minus this first order approximation is controlled by a constant r to the p prime. So we have to do the analysis in 2 different settings. So the hard case, say, is when the gradient is small, right? But in this case, I mean, all the work is already done. So if the gradient is small, say, if the gradient of u at 0 is less or equal than r to the 1 over p minus 1, you just estimate in this way, right? So this is less or equal than the sup of u minus u0 plus gradient of u multiplied by r. For this, to estimate this, you just use the previous result, right? So you get c r to the p prime 1 plus the gradient r to the 1 over 1 minus p. This is the theorem we've just proven. And here, I mean, you just use this fact. So if this is less or equal than this, you replace the gradient of u at 0, the modulus of this, by r to the 1 over p minus 1. Now, this guy plus 1 is exactly p prime, right? And this here, if this is less or equal than this guy times this is less or equal than 1, right? So this is a constant less or equal than a constant. So you get a constant times r to the p prime plus r to the p prime. So you get this, right? And you're done. If the gradient is large, I mean, this is typically the simple case, but the work is not done for this case. So we have to do it now. So if the gradient of u is larger than r to the 1 over p minus 1, we do the following. So we start by defining this number, which is the gradient of u, what is it? It's 0 to the power p minus 1, right? And we do the same type of analysis. So as before, we define this new function, omega, which is u scaled by this factor here, minus u0, constant to the power p prime. And we see that omega at 0 is 0, of course. The gradient of omega at 0, so what is the gradient of omega? The gradient of omega at x is, so it's mu to the power 1 minus p prime, gradient of u, ux, right? So at 0, the gradient of omega at 0 is mu to the 1 minus p prime gradient of u at 0, right? So this is, I mean, since mu is this number, okay, you get gradient models of gradient of u at 0. P minus 1 multiplied by this, so it's p minus 1 minus p. So it's minus 1, okay, times the gradient of u at 0. So the models of